I'm going to start from where we left. We've been talking about properties of data in high dimension. We talked about geometric properties. The reason why we study geometric properties is to bring out the notions of creating empty space, concentration of measures, probability measures, concentration of distances. These are natural properties that occur in high dimension. There is no analog of that in low dimension. So in that sense, the geometry that we have studied, the one-dimensional, two-dimensional, three-dimensional geometries, most of our intuitions are based on 2D, 3D geometry. While most of the properties of geometry holds good, but when you bring in the notion of randomness with high dimension, something strange happens. Remember, that's a thing that we have been talking about. You might think that they're abstract, but I also told you yesterday that it has implications on simulations. How do you want to generate uniformly random numbers in a sphere, in a square? When the sphere, the cube, they are in high dimensional spaces. Today I'm going to start with the concept of covariance estimation in very high dimension. This is of extreme importance to those of you who are working in or planning to work on ensemble analysis. It tells you what are the pitfalls, what could be the pitfalls in computing the covariance when the vectors are very large and the number of data items I don't have very many. And that's exactly what happens in ensemble analysis. I may have a model with a state space 10,000. I may have an ensemble, just 200 ensemble. Generally, we don't have even 200 ensembles, 50 ensemble, 100 ensemble. So we want to estimate the covariance matrix of a state vector of dimension 10,000 based on, let's assume 200 samples. What is that you're going to get? What do you expect? And that's what we are going to talk about. Okay, so let's assume I have IID samples from a distribution with mean 0 and xi's are in RD. Please understand, in statistics, they are always wanting results from IID because they are the basis for everything that we do with probability statistics. The reason we do that is because the theory is neat and clean. If you bring in covariance, the theory becomes more complex. The extreme case of covariance is uncorrelated. So you start the theory with uncorrelation. So there are two related concepts in statistics. One is independence, another is uncorrelated. Independence implies uncorrelated, but uncorrelated does not imply independence. But when you consider Gaussian random variables, uncorrelated and independence are equivalent. I hope many of you who have done basic probability theory have seen this part. So independent is an assumption. Identically distributed is an assumption. Uncorrelated is an assumption. The variables are Gaussian distributed is another assumption. So how various assumptions come to play is what we are interested in. Independence, uncorrelated, Gaussian, uncorrelated, independence are equivalent, so on and so on. So I'm going to get a data matrix, which is D by N, that's the matrix S. So I am generating a data matrix where columns are IID samples from the distribution with the mean 0. All of it may, and I can also assume is identically distributed covariance. Excuse me?
Full screen कर दीजिए. half है ना उसको अगर full होता है.
I didn't understand. Oh, I see.
Oh, maximize करो.
Oh, I see. Okay, good. Oh, thank you. Can you see it now? Full screen. Good. So this is the data matrix as D by N. I want to be able to compute the covariance matrix. To do that, I need to have the sample covariance. The mean is 0. If the mean is 0, the covariance sigma hat, that's an estimate. That's 1 over n times xi transpose. How many of you are with me? Come on, raise your hands, please. Good. So this is the d by d matrix. With me? And 1 over n. You know why that comes in, because we are going to take the inner product of rows and columns. Good. We say this estimate is unbiased if its expected value is equal to the original matrix. And I'm going to assume, and we have already shown that there are several estimates that are unbiased. We have learned things by doing simple problems. So what is the classical convergence theory? The classical convergence theory tells you sigma hat tends towards sigma. If I keep B fixed, let n go to infinity. That means the sample covariance computed using largest sample indeed converges to the true covariance on the assumption D is fixed. That's a classical result. All of it may. I hope you are me. Central limit theorem, law of large numbers. That's the basis for everything that we do. But in general, we may not have infinite samples. And we are considering big data where D is not fixed, but D can be very large, can be fixed, but very large. Yesterday we saw that theory depends on the ratio between D and N. D is fixed, N goes to infinity. D over N goes to 0. D goes to infinity, N is fixed, D over N goes to infinity. D changes, D increases, N increases, but D over N goes to a finite constant, alpha rather than 0. Okay? Both the numerator and denominator, there's a competition, but they increase at the same rate. The ratio tends to a constant alpha. That's an interesting case we are going to be talking about now. So how do you, okay, if I have a sequence of scalars, how do you test for convergence? The test for convergence in mathematics goes as follows. If I have a sequence x1, x2, xk, and so on, in order to show this limit k tending to infinity of xk is equal to x star, what is another way of saying the absolute value of xk minus xn, as k and n becomes large, the absolute value becomes smaller and smaller and smaller. That means the tail of the sequence become indistinguishable. Ultimately, that's the notion of convergence. So how do I measure the difference? With absolute value. Why absolute value? They are scalars. So when you are talking about sequence of scalars, absolute value is a measure of the difference. Now here, what am I talking about? We are not talking about scalars, we are talking about matrices. So how do I measure the distance between matrices? Do you see the reason? Analog, please. If I have points, the distance is absolute value. If it is vectors, the distance is norm of the difference of the vectors. If it is matrices, so I'm interested. So look at this now, convergence. Convergence of a sequence of scalars. Convergence of a sequence of vectors. Convergence of a sequence of matrices. The covariance estimation, we are interested in the convergence of a sequence of estimates of the matrix. So how do I measure the difference between two matrices? The norm. You all know the notion of the norm. Norm measures the size. So I need a matrix norm. Matrix norm comes in various ways. I hope you all remember that in real numbers, one way to measure norm is to be the absolute value. When it comes to vectors, I hope you're all aware that there are very many different norms. One is called the 2 norm. What is the 2 norm? The 2 norm is sum of xi squared to the power half. That's the Euclidean formula, Pythagorean theorem. There's also called 1 norm. What is that 1 norm? The 1 norm is equal to summation absolute value of xi. I is equal to 1 to n. Why 1 norm is useful? Where 1 norm is useful? in electrical engineering, one norm is very useful. Let's suppose I'm having an IC chip. I have different parts of the IC chip. I have to connect the different parts of the chip or wires. One of the problems in IC chip design is that minimize the total length of the wires. Are you in my place? That's right. That's right. And suppose I'm having a city. So this is the two-dimensional plane. This is the city. So how do you measure the distance? This is x1, this is x2. So this distance is d. D is equal to x1 squared plus x2 squared to the power of half. That's the Pythagorean formula. I can also measure the distance between two. So let me say d. This is origin. This is the point A. D comma A. It's given by that. The distance between origin and A can also be measured by sum of the absolute value of x1 and x2. So if I'm going by helicopter, I will fly like this. If I'm going by a taxi, I'll go this way and go that way. There's also another distance, D or A, that is equal to the maximum of the absolute value of xi, I is equal to 1 to 2. That's called infinite distance. This is called one distance. This is called two distance. So in mathematics, we can measure distances in very many different ways. All these ways of measuring distances are equivalent. Right? So in the case of matrices, I need to be able to know how to measure the difference or the size of matrices. I need a norm. A norm for matrix, one norm is called the spectral norm. What is the spectral norm? Every matrix has a set of eigenvalues. The absolute value, the largest eigenvalue, is called the spectral norm. Please, I want you to remember this. A matrix is characterized by its eigenvalue. How many of you remain? How many of you know matrix? How many of you know eigenvalues? So I can characterize properties of matrices by their eigenvalues. So one way would be the two norm of matrices is essentially a spectral norm. And how they measure the spectral norm? It is the supremum is maximum. Supremum is a fancy way of talking about maximum. It is a maximum of a vector. What is the vector? Sigma hat is a matrix. Sigma is the matrix. Difference in the matrix. U is a vector. U is a set of vectors of length 1. So U2 equal to 1 means it is a set of all vectors of length 1. Set of all vectors of length 1 means what? That lie, the set of all vectors that lie on the unit sphere. So if I vary U, so long as it lies in the unit sphere, I can compute this vector. Are you in my place? Everybody. The length of that vector. And the length of this vector changes if U changes. So among all U's that lie in the unit sphere, each U give rise to a vector. Among all the vectors, which vector has the maximum length? Are you with me now? How many of you, please? This is for yes, this is for no. Please don't look at me like that. How many of you name? That's right. Hey, we need to attack ourselves. We need to be able to measure. What are we talking about? We are talking about estimates of matrices. So we need to talk about convergence, not in real space, convergence, not in vectors, convergence of matrices. Concept of convergence is same, but the concept of measuring sizes of the difference is different. Are you with me, please? There are several ways of measuring size of matrices, spectral norm as well. So, under the classical theory, what is it we can show? If D is fixed as n varies, as n goes to infinity, the difference, the norm of the difference between the two matrices tend to 0 as n tends to infinity. That's a precise statement. That's a precise statement. All of you? A measure of the length, a measure of the difference between the two matrices goes to 0. If I have such a result, that's called strong convergence. Strong convergence. This is still classical theory. Now I want to come to the high dimensional effect. Now let n and d grow. In your ensemble, your d has large, n doesn't grow. Most of the ensemble people, they fix their ensemble size to 50, 100, 200, and then say, go 50 samples and then 100 samples. I'm not criticizing. Please don't. Continue to do what you do. Okay? But we need to know the other side of the story. That's what learning is all about, right? What is that I don't know? While I do this, I'm able to interpret this. What is that I may be missing? That's what I'm going to talk about. So it's not a critique. Don't take it personally. I'm just talking about science. Good. So d over n. So this is not what you guys talk about in ensemble analysis. N is fixed, d is large. D over n, in your case, is a number which is very large. D is 10,000, n is 250. D over n, oh God, the alpha is very large. So here I'm considering a case, d over n is alpha in between 0 and 1. Understand? What does it mean? D grows, n grows, d over n tends to a constant alpha, which lies in the interval 0 to 1. Now, I can evaluate sigma hat. How do I evaluate sigma hat? Using the sample covariance. Everybody with me, please? How many of you remember the formula? That's right. Now, if I compute sigma hat, it's a matrix. I can compute its spectrum. What is the spectrum? Eigenvalues. I estimate the matrix. I estimate the eigenvalues of the matrix. Every covariance matrix is positive semi-definite. How many of you know that? How many of you know the definition of a positive semi-definite matrix? Come on, guys. Every covariance matrix has a fundamental property that the eigenvalues are non-negative. If some of the eigenvalues are 0, we call it semi-definite. If all the eigenvalues are positive, we call it positive definite. That's the intrinsic property of covariance matrices. So I'm assuming the lambda 1 is the maximum, lambda min is the minimum. By theory, the eigenvalues are always non-negative. So the minimum eigenvalue is greater than or equal to 0. My spectral arm depends on the largest eigenvalue. Therefore, now let's consider the special case. I'm going to tell you a special case what happens. Something funny happens in here. So the special case goes somewhat as follows. So I have a sequence of random vectors x1, x2, xn. Each of xi belongs to Rd. I compute the covariance matrix, which is a d by d. I'm going to assume these things are coming from normal 0 identity. Are you on the page? I have a vector of size d. Each component of it is mean 0, unit variance. All the components are IID. So I'm looking at a sequence. So this matrix is a d by d matrix. I'm considering a sequence of random vectors drawn from this distribution. Each of the vectors is of dimension d. I have n samples. What am I assuming? By d over n is equal to alpha greater than 0. Everybody, are you all with me? Now, if I give me this, I can compute this. And what is that? This is equal to 1 over n times xi transpose. You all know that. Everybody. I want to go slow because this is of great relevance to those who are interested in ensemble analysis and so on. And I can compute its spectrum. Spectrum of that. I can compute its spectrum of that. Now, please understand, if this estimate is a good estimate, this must converge to pi. Everybody? Why? That is the mother distribution from which I'm taking these samples from. The sample estimate should converge to the properties of the mother distribution. The mother distribution is standard norm. That's what you would expect. That's what you would expect. But please understand, I'm not letting n go to infinity. I'm keeping n fixed. I'm getting d fixed. D is large, n is large. D over m is positive. In that case, if I computed the eigen values of sigma hat, what happens? Something funny happens. The distribution of eigenvalues of I is what? All ones. Identity matrix, who are the eigenvalues? All ones. All eigenvalues are coincident at 1. But look at the distribution. When n is 4,000, when d is 800, and alpha is 2, are you making it? The distribution of eigenvalue is not all at 1, but over interval. Uh-oh. Do you have uh-oh? What's it mean? The norm of the estimate is not the same as the norm of the mother covariance. If the norm of the estimate is different from that of the mother covariance, what does it mean? The estimate is not anywhere near the mother covariance. So here's another example. Are you with me? You must have an aha. It must be an aha moment. So what does this tell you? When d is large, n is large, but d over n is fixed as alpha. If you compute the sample covariance and compute the spectrum of the sample covariance, ideally, all the eigenvalues must be equal to 1, but here the eigenvalues are spread around 1. If the eigenvalues are spread around 1 means what? The two matrices are not equal. Two matrices. What does it mean? The estimate and the true, they differ. So in meteorological circle, what do? I hope you all know that now. They pad. If you look at ensemble analysis, what is the major difficulty in ensemble analysis? Computing the forecast covariance. So the computing the forecast covariance by the sample mean of 200 samples in a 10,000 dimensional space is defective. They know that. They're smart people. So what do? They try to pad. And what is one way of padding? Add a constant to the diagonal. If you can add a constant to the diagonal, then you can make that matrix behave more and more like identity matrix. You can make it more and more invertible. And if anybody knew the formula for the Kalman gain involves the inverse of the forecast covariance. If the forecast covariance is not invertible, you are in trouble. So in order to be able to induce that invertibility, if you look at the ensemble literature within the mathematics axis, there's a lot of massaging going on. The massaging, why do I need that massaging? Because the estimate doesn't have the property that it should. How many of you have been? That's right. I want you to be able to realize this. So, this result was done by two Russian mathematicians. Look at that now. They are mathematicians. They did it in 1967. They did not even anticipate its applicability. It's called Marchenko-Pasteur law. They wrote a paper on called impact of high dimension. So they proved the following. The density of the distribution of the lambdas. What is lambda now? Lambdas are the eigenvalues of the estimates. The matrix is random. Are you with me? The eigenvalues are random. If the eigenvalues are random, it must have a distribution. Everybody plays. Every random variable has to have a distribution. So the density of the distribution of the eigenvalues of the estimate of the covariance is supported on the interval T min alpha T max, where T min is 1 minus square root of alpha square, T max is 1 plus square root of alpha square. If alpha is 0, they collapse. T min is equal to T max. So long alpha is greater than 0, less than 1. You remember my condition? Less than 1. There is going to be an interval which is 1 minus square root of alpha square, 1 plus square root of alpha square. Your eigenvalues are going to lie within that interval. So that essentially tells you, and as a result, when d over n increases and d over n is alpha in between 0 and 1, this result has a non-classical effect. What is the classical result? D fixed n goes to infinity, sigma hat tends to sigma in the strong sense, in the sense of the norm. Alpha, when that condition is violated, and the classical convergence condition is violated, means what? My n is large, but d is large, but d over n is not anywhere near 0. It's better than 0. In that case, we are going to have problems. The problem in meteorology is even worse. Why? We have D is 10,000, n is 250. Are you with me? So you can't expect your estimate to behave anywhere near the real covariance. That's a challenge. That challenge comes largely out of the properties of high-dimensional statistics, high-dimensional probability, and so on. How many of me? I want to be able to tell you, bring out the beauties and challenges of dealing with high-dimensional data. Why is this? Because we talk about big data, right? Every other person now talks about data science, every other person talks about AI, every other person talks about big data. Are you clear? Nothing wrong. Continue to talk, but develop. Okay. Now I would like to give some references. High-dimensional statistic and non-asymptotic point of view. This book has one very good chapter on estimating covariance matrices for various combinations of values of n and p. I don't know whether the library has a copy. Maybe you can order a copy of that book. High-dimensional probability and introduction to application and data science. That's also an extremely good book. So what is the idea here? I know a lot of statistics, but those statistics are fixed D. But here we are talking about statistics where D is large and D is comparable to n. D over n does not go to infinity, does not go to 0, but some other value. I don't know. It is that part is one of the challenges of big data analysis. Of course, I already talked about Cannon's book, Mathematical Foundations of Big Data Analysis. This is the one I passed around. And there's another book, very nice book. You can actually download this free. It's available from Springer. Geometric Structure of High-Dimensional Data and Dimensional Reduction, J. Van. So you can download it. It's also written at a first-year graduate level course. There's a lot of good, interesting results relating to big data, data reduction, dimensional reduction, and so on. Let's look at this now. If I reduce the dimension, then d over n, the behavior changes. So I can bring it to the classical form. And that's one of the reasons why we also talk about dimensional reductions. Some of you might say, hey, in this case, it's applicable only in your special case where xi's are randomly distributed, IID randomly distributed. In my case, the state vector are coming as the model output. Okay? They may not have this property. But what is the exact property and what is the correlation between the various states? I don't know. Are you in my place? So we need to be aware of these extreme results just to be able to tell us that what you see may not be mathematically correct. Are you with me? So with that, I would like to conclude. If there are any questions, I would like to change the topic to clustering analysis. I'm going to deal with clustering analysis today and probably tomorrow. I also have uploaded 3 papers that we have worked on. Each of the papers are PhD dissertations. I will show you as we go back. And if there are any questions on these topics, big data, geometric properties, concentration, and so forth. Oliver, any questions? Is anybody keeping track of the people online?
Just have a check. No questions for us.
Okay, if there is no question, I'm assuming silence implies consent, right? Not always, but sometimes. I always tell the class, cry baby gets milk. If the baby doesn't cry, mother thinks he or she is okay, right? When the baby cries, mother knows that probably he or she is hungry. That's the only way they can communicate. So the only way to ask questions is to ask questions. So if there is silence, I always tell my class, cry baby gets milk. Okay? Yeah.
While preparing the ensemble,
I want to come nearby. I want to hear that. I want everybody to get back to it. Right.
while preparing the ensemble member, what is the use of RSS system?
Yeah.
So how does this background coherence matrix?
You are talking about the process of creating an ensemble. That's right. So what's the question?
Yes, yes, yes.
What is the question?
How's the background coherence matrix?
Background covariance?
Yeah.
Oh,
During each preparation.
that's a loaded question. That's a loaded question. Okay, good. In order to be able to generate ensemble, what is that you need? You need a mean and a covariance. So what is the magic word he used? Background covariance. Correct? So what are we going to assume? There's a state right now. I need to be able to generate ensembles of that particular state. I know the mean, I know the covariance. If you know the mean and the covariance, what is that you can pretend? It is normally distributed with that mean and that covariance. Is it correct? No, there's a little bit of a cheating there. Why do we assume it's normally distributed? Because that's one of the things that we can easily do. Everybody please. So knowing the mean and knowing the covariance itself is not enough. You need to know underlying distribution to be able to generate samples from that. So if you give me the mean and the covariance, I pretend it is the mean and covariance of the underlying Gaussian distribution. Then I have a black box. I can draw from that. Everybody knows how to do that. Now what is his question? His question is, where does the background covariance come from? Is that the question? That's right. In the case of Kalman filter, what is background covariance? It's a forecast covariance. How many of you know Kalman filters? Come on, guys. Right. Let me talk about that for a moment. So computing the background covariance is $1 million problem in geosciences. Are you right? How do we get around it in Kalman filtering? In Kalman filtering, background covariance is called the forecast covariance. Now that he asked the question, I want to talk about it a little bit at some length. I hope you all did. You had a course in dynamic data assimilation not too long ago, did you? Come on, guys. I got a note. And many people who came to lecture are my good friends. How many of you attended that? He knows who attended that, so you cannot bluff him. Oh, you did not take the course. That's all. I'm not trying to find fault with anybody. I'm simply asking how many of you attended that, how many of you knew what went on. Are you with me? I just want to find a test of where you are coming from. The methods for data assimilation in practice consists of two things. One is deterministic method, another is the stochastic method. In the deterministic method, we don't worry too much about covariance, but in the stochastic method, we do. Okay, so what is the basic idea of going from time k to time k plus 1? Let's assume I have the state A at k, A at k. This is the correct estimate of the state at time k. This is the correct estimate of the covariance at time k. A, the superscript A is called analysis. You remember in meteorology, the estimate is called analysis? The posterior estimate in meteorology, they want to call it analysis. There's a Bayesian framework going on. So if I know the XA and XB, what do? I then run the model forward in time. I make a forecast. So I make the forecast of the state. I make the forecast of the covariance in here. So the model pulls it forward. Then an observation comes in. The observation has the covariance RK plus 1. So at this time, I am going to combine the two. That's called the data assimilation. So this is called the forecast plot. This is called the data assimilation phase. What is it, sir? Okay, how do I combine this? That algorithm, Kalman filtering algorithm. So Kalman filtering algorithm consists of your forecast phase plus the data assimilation phase. Everybody. So what is that I assume? So I have to start some place. Initially, I probably assume I know the mean. I know the mean at time 0. I also want to know this. This is called the starting background covariance. This is the covariance at time k. So you can see this is propagated in time. Understand? So to start with, what is it I can assume? You have to be able to compute the background covariance from other sources. If you don't have any other information, pray the Lord and assume is identity. But if you can bring any more information to it, you use that. Let me talk about this now. Do we know the covariance of observations that are coming from satellite? No. Do we know the covariance structure of observations that comes from radar? No. Understand? So what do? Make assumptions about these things. Or you have a project where my aim is to be able to estimate the observational covariance errors and the covariance properties in radar data. That's a separate project in itself. So what is this RK? RK is the covariance of the observation. The observation can come from satellite. So you talk about satellite data assimilation. So this is the satellite measurements. This is the associated satellite covariance. So when those of you who are interested in satellite assimilation, I want to ask you, what do you assume the satellite covariance to be? Those of you who are assimilating radar, what do you assume the covariance of the radar observations to be? All of it in place? That's right. What you gain at the initial background covariance, please understand, the forecasting process did not start today, it started years ago. This is called the sequential method. This is today, this is tomorrow. Today I forecast what the tomorrow will be. Tomorrow came. I have the measurements of tomorrow. So I want to be able to assess xk plus 1 a and pk plus 1 a today. So this I combine it to get this. So the a is called the analysis. So if I have this, then I can make a forecast. The whole cycle repeats. All of you with me, sir? So your question is a good question. It's a good question. The forecast covariance in Kalman filtering plays a role of background covariance. So the model, I can compute the forecast covariance through the model. Then you also have the responsibility of knowing the observational covariance. And you need to combine the two. So knowing the covariance information is the biggest challenge in geophysical sciences. For example, if I have an institute measurement, let's say voltmeter as an example. If you buy a voltmeter, every voltmeter tells you I can measure the voltage from 0 to 200 with 5% accuracy. Have you seen that? That's right. What the 5% accuracy tells you, the standard deviation in the measurements is 5. But in radar, they don't give you that number. For satellite, they don't give you that number. How many of you remain? Please. So knowing the background covariance in Kalman filtering is obtained by computing the forecast covariance. That's one problem. Another problem is knowing the covariance observation is another problem. Have you met? So you need to be able to quantify both to be able to do. So analysis of time k, analysis of time k plus 1. Analysis is always the combination of the model forecast and the observation. Analysis is always better than the model or the observation itself. That's why you do analysis. What is me, sir? Am I giving you a feel for the answer to that question? I also want you to know how, I don't know how many of you know this now. I can make forecasts just based on models alone. I can make forecasts just based on data alone. But if I bring model and data together, if I make a combined forecast, the combined forecast has a better result, has a better quality than the single, any one single of them. How many of you know how to prove it? In other words, why do I do data assimilation? Hey, it's a PhD oral exam question, guys. You're all students, right? You all have to take oral exams. How many of you have seen that? How many of you have pursued data assimilation? Why do you want to do data assimilation? Because say it loudly, I want you to hear.
To improve the forecast so that it's closer to the observation.
It's not closer to the observation. Forecast is forecast. Observation is observation. I have to combine the two to get the analysis. The analysis is better than the forecast by itself or the observation by itself. Do we know how to prove that? I'm going to, well, if there is a need for knowing it, I'll probably do that, even though I wanted to go cross-train. Can I do that?
Yeah.
Okay. Oh, so let me do that, and then after the break, we will start the question. Because there was a question for the floor. I just don't want to leave it by. In other words, from the questions, I believe you need to look at data assimilation in a much more fundamental way. So let me talk about a very simple problem just to fix your ideas. And this is a PhD oral exam question. If after this, everybody should be able to answer that question. Let's assume I have an unknown x. Let m be the mean of the unknown. Unknown is a random variable. It is a mean. Let m be a mean. I want to estimate the unknown. I'm given two pieces of information. One is x1, another is x2. Both are random. x1 has a mean m and variance sigma 1 square. x2 has a mean m and sigma 2 square. I don't know the variance of x. I only know x is a random quantity. Tomorrow's temperature is a random quantity. I know the mean. How do I get the mean? Go to Google. It tells you the climatological average. So the climatological average of temperature in Pune on February 9th, you can always get that. That's the mean. Let's assume. But I want to be able to get a better estimate of that. So I have two pieces of information, x1 and x2. I'm assuming x1 has the same mean as x and x2 has the same mean as x. If not, what does it mean? They're biased. Are you with me? So let's assume the observations that are available X1 and X2 are two pieces of information available. They are unbiased. They provide unbiased information about the unknown X. So I want to be able to compute the unknown. So I have to estimate the unknown by X hat. So X hat is the estimate of X. These are the two pieces of information. So what do? I take a linear combination of the two. It's like a committee's opinion, right? But a committee's opinion, what do? Let's take good part of yours, let's take good part of his, and combine. That's a combined decision. Otherwise, everybody will get mad. Every committee's decision is a linear combination of the decisions of the individual people. I have a committee of two people. I'm going to decide this is going to be equal to A times X1 plus B times X2. A and B are constants. I want this estimate to be unbiased. I hope everybody knows what is unbiased estimate is all about. That means the expected value of X hat must be equal to M. But expected value of X hat is equal to A times expected value of X1 plus B times the expected value of X2. Here I assume the expected value of X hat is M. This is M. This is also equal to M because I have assumed the two pieces of information that is given to me are unbiased. Everybody. Therefore, what does this relation tells you? This relation essentially tells you M is equal to AM plus BM. M gets cancelled, so A plus B must be equal to 1. What is A and B? Are two constants, coefficients. So what is the unbiasedness requires? The constants should be such that they should add up to 1. To begin with, I am already assuming A and B are positive. Therefore, what does this mean? X hat, this is X1, this is X2, this is X hat. So X hat, now A plus B is 1, right? A times X1 plus 1 minus A times X2. Because B is equal to, this implies B is equal to 1 minus A. Everybody, how many heard me? Please raise your hand, nod your head this way or that way. Oh, good. So, in mathematics, what is X hat? X hat is A times X1 plus 1 minus A times X2. That is, X hat is a point on the line segment joining X1 and X2. If A is 0, it is X2. When A is 1, it is X1. When A is in between 0 and 1, it is equal to every point between X1 and X2. I don't know what the real value of A is. Now I want to be able to compute the optimal value of A. Because I wanted to get the best estimate. How many of you saying? Come on, guys, keep nodding, keep asking questions, raise your hands. That's part of the story. Now, how do I want to pick my A? I want my estimate to be unbiased. That fits the condition A plus B equal to 1. I want my estimate to be optimal. Optimal in the sense my estimate must have a minimum variance. Any quantity there's a minimum variance means what? The spread is less. If the spread is less means what? It's concentrated. If it is concentrated means what? Uncertainty is less. I want to be able to reduce the uncertainty in my estimate. I hope you're all me now. So I now need to do the next problem. How do I pick A such that the variance is a minimum? Please stay with me. So the variance of X hat is equal to variance of A times X1 plus 1 minus A times X2. So this must be equal to A squared times the variance of X1 plus 1 minus A squared times variance of X2. How many of you know this? If you multiply a random variable by a constant, the variance gets multiplied by square of the constant. Now, I didn't say it until now because I wanted to wait until that. These two quantities, X1 and X2, are uncorrelated. If they correlate, it means what? They don't tell too many different things. So I always want two independent opinions, two uncorrelated opinions. If they are uncorrelated, the variance of x hat is equal to a squared times the variance of this plus 1 minus a squared times variance of that. What is this? This is equal to a squared times sigma 1 squared plus 1 minus a squared times sigma 2 squared. So variance is a function of a. Sigma 1 squared, sigma 2 squared are fixed. Now I want to make this a minimum. How do I make this a function of a minimum? I have to differentiate this with respect to a, equate the derivative to 0. I want this to be a minimum. The second derivative must be positive. How many have made? That's right. So let's do the derivative of that. So derivative of variance of x hat by del A is equal to 2a sigma 1 square plus 2 times 1 minus a minus 1 sigma 2 square. And that must be equal to 0. Don't copy. Just say the analysis, right? If you copy something without understanding it, then you'll say, gosh, this guy did something stupid I don't understand, right? You'll blame me, not you. But I'm not the one who's writing. You are writing in your notes. So don't put down anything until you know what it is. So 2a sigma 1 squared plus 2 1 minus a. Differential coefficient of 1 minus a with respect to a is minus 1 sigma 2 squared. That must be equal to 0. 2 gets cancelled. Therefore, that's equal to a times sigma 1 squared plus a times sigma 2 squared must be equal to sigma 2 squared. Therefore, my a must be equal to sigma 2 squared divided by sigma 1 squared plus sigma 2 squared. 1 minus a is equal to sigma 2 squared divided by sigma 1 squared plus sigma 2 squared. So what is my optimal estimate? The optimal estimate is sigma 2 squared divided by sigma 1 squared sigma 2 squared x1 plus sigma 2 squared divided by sigma 1 squared sigma 2 squared by x2. Are you all with me? So what does it say? My coefficients must be a function of the uncertainties in the two information that is given to me. What is sigma 1 squared? Uncertainty in x1. What is sigma 2 squared? Uncertainty in x2. What is a? What is 1 minus a? They are all functions of the uncertainties. To how many of you this is new? That's right. Are you with me now? Now, I now know by choice of A, this is an optimal estimate. But I want, now still, x1 is random, x2 is random, so x bar is random. So I want to compute the variance of x hat. Now, in other words, I know its variance is minimum, but what is the minimum value of the variance? How many of you mean? That's what I'm now going to do. So the variance I don't need this either right now. Therefore, the variance of x hat optimum, this is optimum, is equal to, look at this now. This is the constant. This is the constant. Therefore, this is sigma 2 squared divided by sigma 1 squared plus sigma 2 squared whole square times variance of x1. Do you remember the formula? If x has a variance sigma square, ax has a variance a square sigma square. A square sigma square plus sigma 1 square divided by sigma 1 square sigma 2 square square variance of x2. But where is variance of x2? x1, that is sigma 1 square. What is variance of x2? This is sigma 2 square. Everybody. So what is it I can now do? I can take a common factor, sigma 1 square, sigma 2 square divided by sigma 1 square, sigma 2 square whole square. With me? So what is remaining here? Sigma 2 square plus sigma 1 square. Hey, this is sigma to the power 4. This is sigma 1 to the power 4. I get sigma 1 square, sigma 2 square, the common factor. Sigma 2 square, sigma 1 square. So this is whole square, this is this. So these two get cancelled. So this is equal to sigma 1 square, sigma 2 square divided by sigma 1 square plus sigma 2 square. How many of me? Come on, guys. Good. Now I'm going to show you the following. So, x1, what is the variance of x1 is sigma 1 square. What is the variance of x2? Sigma 2 square. What is the combined variance? Sigma 1 square, sigma 2 square divided by sigma 1 square plus sigma 2 square. Now let's verify. Sigma 1 square, sigma 2 square divided by sigma 1 square plus sigma 2 square is less than sigma 1 square. How do I prove that? So I want to check. So sigma 1 square I can cancel. So this leads to sigma 2 square is less than sigma 1 square plus sigma 2 square. Sigma 2 square gets cancelled. 0 is greater than sigma 1 square. This is true, therefore this is true. How many of us made? Come on, guys, please. If you raise your hand, I don't know, you're halfway through. I want to be full through, full throttle. Can you show similarly this quantity is less than sigma 2 square? So what does that tell you? Sigma 1 square, sigma 2 square divided by sigma 1 square plus sigma 2 square is less than or equal to the minimum of sigma 1 square, sigma 2 square. With me? Come on, guys. So what's it mean? My estimate has a lesser variance than the two quantities that went in. You want to have an aha? I'm not forcing you to have an aha. If you're learning something, you have to have an aha naturally. So now what can be x1? X1 can be a model output. Third, what is x2? X2 will be observation. So by combining the model output and the observation in an optimal way, I can get an analysis. Analysis is called optimal estimate. The optimal estimate is random. It's a covariance. That covariance is better than the covariance of the two quantities that go in. That's the reason why you do data assimilation. So if I were to follow your question, x1 is model output, sigma 2 square is the random covariance. x2 is observation, sigma 2 square is the observational covariance. By combining the two in an optimal fashion, this is the simplest example of illustrating common factors. Are you with me? To how many of you this is new? Guys, to how many of you have an aha here? So you can pass at least one exam, one question in your oral exam. Why do you do data assimilation? It's not necessarily to pass the oral exam, but this is a fundamental result in data assimilation. Why to bother? Why to bother? We are coming on 11:02. The tea is hot. I don't want to hold you for too long away from the hot tea. Are there any questions? We may have one of a couple of minutes. If there are no questions, let's take a break. We will come back at 11:30 sharp. I'm going to start the next topic. The next topic is a topic in data science, a topic in AI, a topic in learning. Let's call it class. We will do that right after break, 11:30. Thank you. Right.
Example. Yeah.
Cool.
It has less but I don't retain
Close it and then we'll start. Here's the file name. You can make it. Some engine in the back.
No, no, not because it was in a pen.
So it's like, yes, it doesn't work.
The ratio is not.
Maybe if he does you cannot say anything.
So it's like,
No, but it's myself, no, this year, Arya, she's one and one of years. It still is, yeah. No, no, in our batch, we were like 5, 6, 7, 8.
don't know how to access the YouTube channel. Okay, I'll probably ask you to write this down. So I can use that one if I need to. If I need to, we can probably change it. Then you can use this. Hello again. I'm sure each of you have several questions to ask. All questions are important for me. Just like background covariance, these folks asked about where the dimensionality becomes high and so on. So what I'm going to suggest to you is you keep all your questions. Friday, second lecture on Friday, we will have question answer session. It will be my own exam. You will be asking the questions. Are you okay? So please bring your questions. The last class, the second lecture on Friday, we can devote totally to that. But I'm supposed to cover new topics. So the topic I'm going to cover is called multivariate data analysis, tools for data mining. The topic I'm interested in is called clustering. So what are the basic tools here? Clustering, principal component analysis, time series analysis, similar spectrum analysis, discriminant analysis, pattern recognition and learning. These are the topics of great interest within AI. So this is the outline of the talk. I don't want to spend too much time because I'm going to give a talk back, so we don't have to worry about that part. So I'm talking about clustering. Yesterday I told you that we were given a research problem. It's a 25-member ensemble. The 25-member ensemble was created by basically 4 models with different physics. The same model, you change the physics. The same model, you change the different initial conditions. So using 4 models and a variety of physics parameterization, they created different initial conditions, a total of ensemble of 25. They ran the model forward in time for 72 hours, 128 hours, and so on. They wanted to see how the model responses behave. So that was a clustering problem. I will come back to these conceptual things, which may not mean much right now, but we do it something and then we'll talk about classifications. Okay. So what is the starting point? The starting point for clustering is the data matrix. I have n objects. Each object is going to be measured in m attributes. M is the number of rows, n is the number of columns. In the case of model ensemble that I talked about, m was of the order of several thousands. The model output across a domain. Right? N was only 25. So I have long vectors, each representing the model output at different times. These folks asked me a question before we started. I'm going to start with that because I want you to have a good feel for where the M gets large in the context of models. Suppose I have a domain. I grid the domain. Let nx be the number of points, let ny be the number of points. Let m is equal to nx times ny. I have a PDE that I discretize in here. So that at each node there are values. At each node there is pressure, temperature, humidity, U, V, W velocities, and whatever quantities. So there are n quantities of each of these variables. That's called a state vector. So let's assume there are L variables. What are L variables means? Temperature, pressure, humidity, 3 velocities. let that be L. So I'm going to have a vector of size m which is equal to m times L. Everybody? This is at a given time. So the model output comes across this at a given time. The model output is computed every 10 minutes for 32 hours for 128 hours. There are 25 such models. Are you with me, please? That's right. So there's a matrix for pressure, there's a matrix for temperature, there's a matrix for U velocity, V velocity, W velocity, humidity, and whatever else the model can calculate. Yeah.
Please can you repeat? What is M?
I want to hear you. I can't. Okay, go ahead.
What is M there?
M is the size of each vector. I'm now trying to give you a feel for what that M is. M is equal to N times L. N is the number of grid points. At each grid point, I'm going to measure L variables. So M is N times L. There are 6 physical variables. Nx is 100 points, Ny is 100 points. 100 times 100 is 10,000. 10,000 times 6 is 60,000. At each instant, the model, every ensemble run, gives rise to a vector of size 50,000 every seconds, every hour. So, you got it?
So then M will is M to
Oh, M is equal to N times L.
okay.
No, you probably didn't see that very well.
20%.
Yeah, M is equal to N times L.
But there is another variation.
One thing. The M is equal to N times. Okay, I don't want you to confuse that N with this N. So let's call this capital N then.
There another variation is.
One second. Let me make sure I understand him and then we will discuss. You've been a capital N is the number of grid points. At each grid point there are L variables. M is equal to capital N times L. N is the number of sample runs. So the matrix I was given was of this type. Yeah, go ahead, sir.
Sir, actually, this is for one particular layer.
What?
Most of the variables are three-dimensional.
Absolutely, absolutely. I'm only considering
vertical direction also.
that's right. I'm only considering a 2D right now. If it's 3D, stack one on the top of the other. Sure. So in that case, what it will be? It will be my N will be equal to Nx, Ny, Nz. My M will be equal to N times L. So the big problem gets bigger in a hurry. You go from 1D to 2D to 3D. All of you? So most of the problems here, Jason says, are all big D, big data by its very nature. Are you with me?
Yes, sir.
That's right. So physically speaking, I still have a function x, y, z, and t. But that's continuous. But I'm sampling. A grid always samples the continuous variables. Are you with me? That's right. That's right. Good. So for my case, that B applied, I will show you. M is very large, N is small, 25. It could be 50, it could be whatever you want to talk about. Yeah, thank you. So that is a data matrix. Okay, now let's talk about this now. In psychology, I come from applied mathematics. I have to talk to psychologists as well as meteorologists. In psychology, what do? They collect data. How do they collect data? By doing surveys. A survey consists of questions. So a survey consists of YAM questions. I give survey to everybody. There are YAM different responses on YAM questions. I create the matrix. So what is the challenge in psychological or sociological survey? How do I make sure my questions are independent? Am I asking the same question in different ways? A lawyer in a court to check how stable you are will ask the same question in different ways at different times. And if you slip once, the case is over. Are you with me? You are contradicting yourself. So you are not a worthy person to believe in. Because yesterday you said that, today you said this. What is the truth? He can neutralize you very quickly. Are you with me, please? So in psychology or social science, they want to find out what is the minimal independent set of questions, or how the questions are correlated. Are you there? You can drop the questions with a high correlation. So what is the other analysis? Given a set of attributes, how the objects are correlated. So I can talk about correlations among features. I can talk about correlations among objects. Correlation is the key. So another way of looking at the correlation is similarity. For example, we all say that, right? Humans are the same when it comes to animals. But humans, men and women, I already gave you the example in the last couple of classes. Oh, he looks like a Japanese. He looks like an Indian. He looks like a European. Don't you say that? How do you do that? We have an innate capability of trying to distinguish objects. That's the ability to discriminate, the ability to distinguish, the ability to understand similarity. To be able to discriminate, I need to know the opposite of discriminate is similarity. So if I want to be able to classify objects, I need to be able to classify objects based on similarity. So classification is a simplest of the topic in learning. It's called unsupervised learning. Unsupervised learning. So I can classify objects, I can classify attributes. In psychology, they are interested in classification of attributes. In other sciences, we are interested in classification of objects. So I'm going to obtain the data matrix. In the case of numerical, in the case of method prediction, it'd be running the model forward in time. 25 models forward in time. And each time I have a matrix of this type. In opinion survey, I create a question, I wait for 2 weeks, I collect all the questions, I create a matrix. So first step is collection of the data matrix. Now, what are the properties? Each column refers to an object. Are you there? Each column refers to an object. Each row refers to the features of different objects. For example, the height of everybody, the weight of everybody, skin color of everybody. Are you with? So the rows, the elements in the row, they all have the same units. The elements in different rows have different units. One is height, another is weight. So the rows are features across all objects. Columns are all the features of a given object. I want you to be able to distinguish all the features of a given object, a fixed feature of all objects. Rows, columns. Rows, columns. Are you there? That's right. I'm now going to illustrate the clustering algorithm using a very simple example. Like, I need to have a simple example to visualize. Okay? So let's talk about simple problem. I have 5 objects. Each object is measured across 2 attributes. Because it's 2-dimensional, I can represent this distribution. Sorry. So the same example, I have 5 objects, 2 attributes. I can consider each coordinate x1, x2. So 1 is 10, 5. 5 is 5, 10. 4 is 30, 15, and so on. So what is it I have? I have 5 objects or 5 points in a 2-dimensional space. Everybody. In general, I have n objects in a m-dimensional space. M is 2. I want to be able to visualize the larger problem from a smaller problem. What's my goal? My goal is to be able to cluster. So what does intuition tell you? Even without doing anything, if you show this to a child, if I show this to somebody who has not even gone to college, ask them which one are similar, what will they say? 4 is very close to 3. 4 and 3 are similar. 1 is 5, they are very similar. 2, probably different, but if you push me, 2 is more similar to 3 and 4 than 1 and 2. Oh, I'm sorry, 1 and 5. Can we say that? That's intuition. So whatever I'm going to do mathematically must conform to my intuition. That really for mathematics. That's a touchback for mathematics. Mathematics should be able to help and corroborate the intuition. So I'm going to develop a class of mathematical techniques using which I want to uncover the underlying similarity between objects, because I want to classify objects based on similarity. Right, me? So now let's talk about how we measure similarity. Similarity can be measured in many ways. If two objects are correlated, they are very similar. Objects are what? Objects are represented by vectors. If I have two vectors, if the correlation between the vector is large, then they are very similar. If the correlation between the vectors is very small, then they are less similar. Another way of measuring similarity is how, if this is the vector, this is another vector, the angle between the two vectors. The cosine of the angle between the two vectors. If the angle between the vectors is small, cosine of the angle is large, because cosine 0 is 1, cosine 90 is 0. So by measuring the angle between the two vectors, I can measure the similarity. The smaller the angle, more similar the vectors are. Larger the angle, less similar the vectors are. So correlation, cosine of the angles. The third one, distance. If a vector represents a point. If the distance between 2 points is large, they are less similar. The distance between two objects is small, is more similar. In other words, distance is a dissimilarity measure. Correlation and the cosine of the angle are similarity measures. How many of you think? If I want to classify, I need to uncover the similarity. So we want to first settle on the notion of similarity, how I'm going to measure similarity. Similarity can be measured one of three ways. One is correlation, another is cosine of the angle between the two vectors. Do you know how to find the cosine of the angle between two vectors? No problem. I hope you all remember the formula from basic geometry. Hope you remember the formula. Inner product of the two vectors is this. So what is cosine of the angle? Cosine of the angle theta is equal to inner product a comma b divided by norm of a times norm of b. So I can compute it. I can also compute the distance. So the distance between a and b is equal to summation ai minus bi. I is equal to 1 to m. What to the power half. That's the distance. So if the distance is large, is less similar. If the cosine of the angle is large, it is more similar. So I can measure similarity like this. Everybody?
One square is it?
Excuse me?
AI minus BI square to be perfect.
But
AI minus BI only is the some square should be.
so this is the distance. A is a point with coordinates. B is a point. It is the difference between the coordinates. I'm sorry, you are talking about the square. Yeah, you are right. I forgot the square. You are right. The square of the difference, the sum of it, square. Thank you, sir. That's right. Are you understanding? So I have to pick and choose. What am I going to do? I'm going to pick the distance measure. I'm going to illustrate the method of classification by choosing the distance to be the measure by which I'm going to capture similarity with the proviso, the smaller the distance, more similar, larger the distance, they are less similar. Is the problem clear enough? I don't have any other information. I only given the data. From the data, I have to infer who are all similar to each other. There is no external teacher. So that's why it is called unsupervised learning. I have to classify them based on the properties of the given objects. I hope you're all with me. Any questions on this, please? So collection of data matrix, I'm not worried about it right now. That's a pre-processing. Then choice of similarity measures. Here, some comment. Suppose you measure the length in millimeters, the value will be very large. If you measure the height in terms of meters, the number will be very small. The scale of measurement of the individual attributes is going to affect the magnitude of the measurements. So if I have a vector where some coordinates are very large and some coordinates are very small, if you compute the distances, the smaller guys don't have any say. The larger guys dominate. And why does that happen? Because your elements of the vectors are very disparate. They are very different in sizes. In such cases, what is that you need to know? You need to normalize. You can divide every element by the norm of the vector. You can divide every element by the maximum of that. All in the place? This is something we all do. That's called non-dimensionalization in one way. That's called scaling in another way. Scaling, non-dimensionalization. These are all various tricks by which we bring the quantities of interest in computation to be in similar ranges so that no one guy will take the show off. Okay, so I'm assuming based on the values, I already normalized. So I have a normalized data matrix. The example is this. So what's the first thing I want to do? I want to be able to compute the pairwise distances. There are 5 objects. I need to be able to compute the pairwise distances. So let's go back. So that's what's called similarity, means resemblance, right? So similarity matrix is also called resemblance matrix. So given the data, from there I need to be able to compute the matrix called resemblance matrix or similarity matrix. What does that say? S21 is the distance between object 2 and 1. Okay? The distance between object 2 and 1 is the same as distance between object 1 and 2. The distance between object 1 and 1 is 0. So the resemblance matrix is a symmetric matrix. The diagonal elements are all 0. Therefore, I need to consider only the lower triangular part. S12, S13, S31, S32, Sn1, Sn2, Sn minus 1. Everybody. How many of you with me? And this is going to cost money. If n is large, I have to compute a lot of things. So given the data matrix X, you extract this resemblance matrix, yes. The given data matrix is rectangular. This matrix is a lower triangular part of a square matrix. A square matrix gives you all the information about the similarity measures. The algorithm we are going to talk about never sees the input data. It only works on the resemblance matrix. Okay? So what is the first step of the algorithm? I'm going to illustrate the algorithm step by step. So for the 5 objects in question, you remember, I have to compute the distance matrix. Everybody? I want you to believe me, but at the same time, I want you to check me. Don't take me for granted. I want you to do this. I don't know how many of you know this Chinese problem. I tell my class, you hear, you forget. You read, you remember. You do, you understand. Are you with me? I want each of you to type this in bold letters and put it in your study. You need to hear. You remember we say, karaoke, I don't remember, I heard something like that. To spread the rumor, we say that, right? Good or bad. So you hear, you forget. You read, you remember. You do, you understand. So you can never say I understood until you do it. So to say no is to be able to know to do it. Understand? So it will all look nice. The whole question is this: after the seminar is over, can you do it yourself? So I want you to be able to do this problem as a simple problem with a calculator. You should be able. Don't write a program. When do you write a program? Only when the problem is too big and you know how to do it. Understand? Everything you should be able to do it yourself. Simple problems. Once you understand, once you are able to do it, then you can depend on programs and other things. So I want you to check each of these calculations as I go by. So there are 5 objects. There are how many combinations of how many pairs out of 5 objects? 5C2, the number of combinations of 2 taken out of 5. That is 5 times 4 divided by 1 times 2, 10. Are you with me, please? So 4, 3, 2, 1, that is 10. So there are 10 parallelized distances I need to compute. I computed them in here. Now, what do I look for? I'm looking for 2 objects that are closest because I'm using distance measure. So what is the smallest number here? 5. So what does 5 tells you?
3 and 4.
3 and 4. I'll look at that. Do you go back to your intuition? 3 and 4 are closer to each other. Is the theory jiving well with your intuition? So what does this say? I can now bring 3 and 4 together and make them into one group. So originally I had 5 individual members, 5 groups. Clustering involves putting people together. I want to put people together who look more similar. And that's what we do. That's what we do. Don't we? That's right. We are able to distinguish the dog breeds. How many different types of breeds? All the dog owners can essentially, by the look of a dog, they can tell you which is this type, which is this type, which is this type, which is this type. Cars, horses, humans, plants. Look at classification is there everywhere. Biologists do, zoologists do, everybody does. So within the parlance of sciences, the classification algorithm began in social sciences about 50 years ago. Argument? It's not right. Not right. So now I'm going to bring 3 and 4 together. So originally I had 5 objects, 1, 2, 3, 4, 5. I'm going to put 3 and 4 together. So now I'm left with only 4 objects. 1, 2, 3, 4, and 5. Everybody? Yes. Good. What is the next one? The next one is the following. I want to be able to compute the distances. So here comes a little doing now. So originally I had 1, 2, 3, 4, 5. Now I have 1, 2, 3, 4, and 5. So what's the question? How do I compute the distance between 2 and 3, 4? How do I compute the distance between 1 and 3, 4? How do I compute the distance between 5 and 3, 4? The distance between 1 and 2 has not changed. The distance between 1 and 5 has not changed. The distance between 2 and 5 has not changed. So we are now facing a new problem. What is the problem? While I know how to compute the distance between 2 individual points, now I'm called upon to find the distance between a point and a set. Are you all me? Yes. How do you do that? There are very many ways of doing it. So let me talk about that now. So here is a set X. Here's a point X. Don't confuse this X with any of the other X's. So this is Y1, Y2, let's say YK. So let the set consist of K points. Let there be a point X. I want to be able to define the distance between X and S. several ways in which distances can be measured. You are limited only by your imagination. In mathematics, how do they define the difference between set and a point? In mathematics, they define it to be the minimum of the x, y, where yi belongs to s. You compute the distance between x and y1, compute the distance between x and y2, compute the distance between x and yk, the minimum of that. I could also compute this as a maximum yi belonging to s of the xyi. I can do many things. Yeah, that's the beauty of mathematics. You can do many things, but you have to be consistent. What's the third one? The third one is as follows. Dx yes is equal to 1 over the number summation dxyi, I is equal to 1 to k. What does that tell you? You compute the distance from x to each of the yi's and compute the average. Everybody be pleased? It is the average of the distance between point x and every other point in s. It could be minimum, it could be maximum, it could be average. If it is minimum, only 1 point decides that. If it is maximum, only 1 point decides that. If it is average, everybody contributes to that. The average is democratic. Are you with me? So in my analysis, I'm going to pick this to be the definition. It's called pairwise average distance between point and a set. How many of you are with me? You all have an aha here. So I have finished the first iteration. I found that 3 and 4 are close together. Now I want to go to the next iteration. That brought a new point. The new point being define the distance between point and the set. I solved that point of the problem by picking a choice, the choice I like. Why do I like that choice? Because everybody has some say in it. Good. So with that in mind, now I'm going to compute the distance. What are the distances now? 1 to 2, 1 to 5, 1 to 3, 4, 2 to 5, 2 to 3, 4, and 5 to 3, 4. Everybody? Yes. I compute these distances according to the formula. That's what I got. The number of objects used to be 4 or 5. Now they become 4. But 3 and 4 are the same group. So look at that. Everything else remains unchanged. The last thing changes. Because 1 to 3, 4, 2 to 3, 4, 5 to 3, 4. This one, this one, this one, computed by this formula, the average. All of you? Yes. Now, I have to pick something which is minimum here. Which is the minimum? 7.07. 1 and 5. 1 and 5 are similar. Let's go back. Hey. First, I looked 3 and 4 are similar. Then we thought 1 and 5 are similar. My algorithm is consistent with my intuition. You may say, it's like a tried example. Yes, it's like a tried example. But you got to get the ball rolling somewhere, right? If the algorithm does not make sense in the contrived example, it won't make sense in a real world problem. If the algorithm makes sense in the contrived problem, there's a good chance it will withstand the pressure of the real world problem. In fact, it does. Okay? So what is the idea? Whenever you are interested in solving a problem, don't crash against big problem. Try to scale down. What is the simplest version of the problem I need to understand to solve? If I don't understand this problem, how can I solve that problem? Are you with me? So what is the proverb? You have to learn to walk before you run. A child cannot run until he or she walks. You have to learn to walk before you run. Always solve the simplest version of a given problem. Once you understand that, then you can very easily scale down. And that's exactly the point. That's exactly the point. All of you been? Good. I have shown all the calculations. I have decided 1 and 5. Now look at this now. 5 became 4, 4 becomes 3. I have 5. I'm sorry, I have 2, 1, 5, 3, 4. Uh-oh, I have a big problem now. I have to compute the distance between point and the set, point and the set. I also have to compute the distance between set and the set. So let's now talk about that. So if I have a set S1, if I have a set S2, so how am I going to define the distance between S1 and S2? It is the sum of, I hope you all remember the following notation. Yes refers to the number of members of the set. Number of members. Absolute value of a set is equal to is called the cardinality of the set. Cardinality of the set essentially tells you the number of members of the set. How many of it may? That's mathematical notation. So I need to be able to compute the distance between xi, yj, I belonging to S1, j belonging to S2, 1 over S1 times S2. So this is the total number of points in S1. This is the total number of points in S2. Using this, I can now verify. I want you to verify this. Please, you got to go home and do all the calculations and verify that. Then you'll understand total. Now, which is the smallest? 12.7. What does it mean? 2 is similar to 3 and 4, rather than 1 and 5. And that is bound by my geometry. Remember, the distance between 2 and 3, 4 is smaller than the distance between 2 and 5. So 12.17 is the minimum. So what am I going to do? 5 became 4, 4 became 3, 3 became 2. All of you? Yes. I'm trying to pull them together depending on cluster. So 1 and 5 look similar, 2 and 3 look similar. Now what is the distance between them? 2 sets? 21.6, there is nothing much to choose? Perhaps. Are you with me? Yes. So that tries to give rise to the tree structure. This is the end result of my cluster analysis. Let me tell you, at the topmost level, all humans are same. We all have same features, don't we? But if you look at microscopically, we are all different. So at what level you want to be able to compare cluster? So now, at the x-axis, I label the objects. At the y-axis, I'm labeling the distance. If I say 2 objects are similar, if their distance is 0, then there is no similarity between any of them. They are all 5 clusters. Are you with me? How many of us may? That's right. But I'm willing to tolerate. What do we say? The North Indians have certain features, South Indians have certain features. I don't want to get into the controversy, but this is something we all talk about, right? Japanese people look different, Chinese people look different. Indians look different from Tibetans. Don't we say that? Yes. Come on, guys, I'm not saying anything you don't say at home. I'm not trying to discriminate. I'm trying to tell you a conceptual things. So if I'm willing to absorb all differences, all humans are saying, what does it mean? I'm willing to ignore the individual differences. If I'm going to be microscopically looking at all the differences, no 2 are alike. So that's the scale. At zero distance, everybody is different. But if I express my tolerance by allowing distance, if I say I'm willing to tolerate up to a distance 5, then 3 and 4 look alike, everybody else different. If I further relax my tolerance to 7.07, these two guys are already similar. New similarity is born 1 and 5. If I'm willing to tolerate further at 12.7, these 3 guys look similar. That's different. If I'm willing to tolerate at 21.7, all look alike. Isn't the way we do business in our? That's fine. All of you?
Yes.
So this is called tree diagram. This is called dendrogram. It is the result of my clustering exercise. This is called hierarchical clustering. So if I want to answer the question, how many clusters? Then the algorithm does not answer that question directly. You have to tell me the level of tolerance. If I say the level of tolerance is 6, I draw a horizontal line at 6. If I draw a horizontal line at 6, there are 3 clusters. Okay? If I drew a horizontal line at 20, there are 2 clusters. Okay? So this algorithm doesn't make the ultimate decision of how many clusters, but it provides the framework for you to be able to compute the different clusters. So you need to bring in to the table your own perception of the level of tolerance. So if you push me, what is that I will say? Either 2 clusters or 3 clusters. If it is 2 clusters, what are they? 2, 3, and 4, 1 cluster, 1, 5, 1 cluster. If it is 3 clusters means what? 3, 4, 1, 5, 2, 2. So in this problem, I don't know exactly what the answer could be, but there are either 2 clusters or 3 clusters. How many with me? So I have learned something about the objects. I have learned about the similarity. I have learned to classify them. I have a large number of objects. I'm able to combine them into smaller groups. That's one of the typical problems in classification. This algorithm is called unsupervised learning. What is supervised and unsupervised? You go to cooking class, there's a master cook who teaches you how to cook. If you want to learn piano, there's a piano teacher how to play piano. You want to learn swimming, there's a swimming teacher. So most of the things we learn are learning with the teacher. They are called supervised learning. That's why you have to pass the exam. Okay? In supervised learning, how do you test it? You have to pass the exam. Those of you who have done some neural networks, you can teach the neural network, but what is the real test for neural network? It has to classify objects and things it has not already seen, but the ability to generalize. That's equal to passing the exam. Unsupervised. Some people with no interaction, they can play guitar. Have you known? Do you have friends like that? Sure, I have. Some people, without anybody, they can play piano. Are you doing? Yeah, that's right. Ramanujan never learned mathematics from anybody, but he could solve many problems. So many of us are learning things under the supervised framework. Genius. He can be a genius chef. He can be a genius basketball player. He can be a genius musician. He can be a genius anything. I admit, those genii, they don't depend on anybody. They have intuition they can develop. That's unsupervised. But those of us who learn to sing, to cook, to swim, to drive, is also right. So here, nobody tells you, I postulated the measure of similarity, and the algorithm, simply based on the similarity, helps you to trust it. So the algorithm has the intelligence of a human being. The algorithm exhibits unsupervised learning. Are you there? Yeah.
So, but
Okay. No. First say aha. It's opposite. Have you seen that concept here? You ask a question, but you did not acknowledge the answer to the previous one. Come on, guys. That's money in the bank. Understand? You first ask a question. Somebody answers that. Yes, I got it. Now may I have a continuation of the question. Don't say but. I got it, but. I'm not trying to criticize you. But this is a general concept, right? That's right. So enjoy the moment. That's what I'm trying to tell you. The first question is answered. I got it. I have a follow-up. Say follow-up. Good.
But we are given the threshold. We are considering the threshold.
No. The threshold nobody gives you. You have to decide.
Yeah, I am deciding. So in my algorithm, I am deciding because I am deciding.
Sure. Because there could be many thresholds possible.
Yeah, so I am deciding 7.07. So I am getting.
No, you are not deciding 7.07. 7.07 was the minimum in the matrix.
Okay.
You say okay again. Okay, fine. They are all dull answers. Aha. Come on. Have you seen the way we talk? If you ask a question, how are you? Fine. They won't even ask back. I'm fine. How are you? Are you there? If somebody asks you, how are you? What do you say? I'm fine. Fine. I'm fine. How are you? This is okay. I have a follow-up question. Enjoy the moment, guys. Life is short. Don't go too fast. Please go ahead. So let's come back here. The threshold 5, who decided it? I didn't decide. It's the minimum of the distances. 7.07, who decided it? You didn't, not I did. It's the minimum of the distances. Who decides the minimum of the distances? The data. The data speaks. A good question to ask. Why is the threshold? 7.07 is the threshold, 12.7 is the threshold, 21.6 is the threshold. Who did it? The data. It's the minimum of the entries in the lower triangular part of the similarity matrix. Are you with me? That's why it's unsupervised. So what is the only thing this is predicated on? Let the distance be a measure of similarity. Smaller the distance, more similar. Larger the distance, less similar. That's the only rule. That's the mother of all rules. And that rule drove the algorithm to move forward up until I got this tree. So the tree structure, why this is called hierarchical? Because I can get a variety of clusters by cutting it. Cutting it, that threshold, that's human input. Are you remembering? That's you need to decide. Hey, you cannot automate everything right in life. You have to be human interaction. To you, 3 may be a good level. To him, 7 may be a good level. To somebody else, to some other problem, 11 could be a good level. It depends on what the problems are. It depends on what your perceptions are. It depends on what other considerations are. So this doesn't take away your ultimate responsibility, but gives you everything in a silver platter. Understand? The tree is a silver platter. I give all the results. Take it from here. It is totally data driven. That's our question. Are you with me? Any questions? Any other question?
One similarity is
Okay.
our human brain also works in that way actually.
Yeah.
Whatever actually we are doing in here mathematics, that actually human brain is the brain.
This guy was traveling my train. He was just the opposite gate. That guy sang very well. I enjoyed the music. He looks like from Tamil Nadu. Let me say that. That's right. That's right. That's right. That's an example. So what is the human intuition? What do humans do? Trying to mimic what humans do is intelligence, is artificial intelligence. So one of the simplest form of algorithms in artificial intelligence is unsupervised learning classification. To me, I told you yesterday, Twinkle Twinkle Little Star is the first lesson in every music class. This is the Twinkle Twinkle Little Star of AI. Unsupervised learning. Are we done? No, there are lots of other things we need to talk about, but I want to bring back the concept very quickly in here. Are you there? So what are the various things now? If the measurements are very far apart, I have to normalize. What are the methods of normalization? Are you there? So I do all these exercises. This is available to you. Please talk to Vinu or whomever has access to this machine. I want each of you to be able to download all the things with you. And what's the best way to do it? Print it. While printing and reading it, I have to write the notes. In the paper itself, you work it out. Don't postpone. Don't postpone. Are you with me?
Yes.
Then, gee, I have learned so much. This is my knowledge. Remember the Chinese proverb? You do, you understand. Okay? Yes. So, what is the theme of cluster analysis? I'm given a data matrix as an input. Cluster analysis process, clusters. The cluster analysis process, what is it contained? You extract the similarity. The algorithm helps you to club objects into sets based on similarity.
One question.
Ah.
If there are some outliers, means say point is far away from all other points. So will you give that weightage to that point?
We can normalize it.
We have
And
to bring it to close.
Yeah. That's a good question. If the value is large, what do you mean by it will be outlier? Do you believe the outlier? That again depends. If you believe it, you have no way of justifying it through it. Or you include it but normalize it. So that's not one solution, that's many solutions. If you have lots of data, you can afford to throw it. A small number of data, oh, you can't throw it out, right?
That happened to the Einstein when he has actually developed the theory of relativity.
Sure.
Most of the scientists didn't agree to
That's
that,
right.
but afterwards they acknowledged.
Sure. So along that line, I'm now going to talk about scales of attributes. There are different kinds of scales. One is called the nominal scale. An attribute A and B are two objects. So on that attribute A, the score for A is XA, the score for B is XB. The attribute will be height, weight, eye color, whatever. So XA is the value of A for A, is the value of the variable for object A, XB is the value of the variable for object B. Yeah, a variable is said to be in the nominal scale if I can test only equal or unequal. For example, skin color. What do you say? Black, brown, white. I don't want to say anybody else. My color is brown. So black is not equal to brown. Brown is not equal to white. But I cannot say white is better than brown and brown is better than black. Even though societally we all consider that, right? We want our children to be milky white.
How do you define, because it is subjective, which
I did not even finish. Hold on, I'm going to ask you, let you ask the question. I'm going to finish. So what is that? So a variable like color of the skin, I can only test whether equal or unequal. There is no addition, subtraction, multiplication, division. I cannot perform any other operation. If variables are such that I can either count quality, they are called variables in scale. For example, in a survey, they ask you, what is your gender? Male, female. Male is not equal to female, female is not equal to male. Male is male, female is female. I cannot say male is better than female, female is better than male, and come back and meet my friends tomorrow. Nobody will talk to me. Right? So we can only test by equality. We cannot even compare. That's how we're doing arithmetic. So if a variable is such that you can only test by equal or unequal, they are called variables in nominal scale. Yes, ma'am.
Sir, I'm asking that color is a subjective variable. How do I define
Why do
that?
it may be subjective, but I'm trying to ask you, in an application form, tell me the skin color, what do you do?
That's why I'm asking that whether my color is browny or black, what is the level of definition of
I don't know that. You have to decide because you are filling the application.
We can give the wavelength.
That's right. We can't give the wavelength. That's right. Are you there? Color of the hair. What do you say? Color of the eyes. What do you say? Are you there? That you have to call. Once you call, I'm not going to question you. But that definitely works. I have no difficulty. My color, my hair is white, my skin is brown, my color eyeglass is black. In fact, my grandson, I have a granddaughter and a grandson, the joy of my life. My grandson, once in a while, will ask me, how come in Tamil, Tata is grandpa? How come Tata's hair is always white? My grandfather would say, his hair is always white. Are you there? That's right. So your child knows how to characterize the colors. Are you there? So you call it. It may be subjective, but I'm going to believe what you say in your application or in your form. Okay? So gender takes male, female. Colors of a rainbow takes only 7 colors. I cannot say this color is better than that, even though we all say, my favorite color is blue. Favorite. That's not better. Are you there? One. It's called ordinal scale. Nominal scale, ordinal scale. We want to rate a movie in a scale of 1 to 10. Are you there? We know rating 5 is not equal to rating 2. We also know rating 5 is better than rating 2. So here you can test for equality and also you can order. Grades in exam A, B, C, D. A is better than B. C is better than D. But you don't know whether A minus B is the same as B minus C. Do you? I don't. Nobody does. So I can only say either they're equal or unequal. I can only say something is better than the other, but I can't measure the difference. You see that now? So there are variables of this type. So in these variables, there is no addition, there is no multiplication, there is no subtraction, there is no nothing. Now, variables in the interval scale. XA is greater than B. In the scale, XA minus XB makes sense. Today's temperature is 10 degrees warmer than yesterday's. But I'm going to measure temperature in centigrade scale or the Fahrenheit scale. We arbitrarily put at 32 or 0. But what is the real absolute, real 0, absolute 0? So temperature measured in the absolute scale have a different property. Temperature measured in the centigrade or Fahrenheit scale are defined with respect to arbitrary origin. 32 the origin, 0 is the origin. But the real origin is the absolute 0 for temperature measurements. Are you making it? So variable measured with respect to arbitrary origin are said to be of the interval time. So temperature is an example of that. One is called the ratio scale. He makes twice the salary as I do. He's very happy. She said that. The difference between his salary and my salary is 20,000 rupees. You see? His salary is better than mine. His salary is not equal to mine. So salary, I know 0 salary means that is the origin. Like 0, absolute 0 is the 0 for temperature. Are you with me? So Variables measured in the ratio scale, you can do addition, multiplication, subtraction, division, comparison, check for equality. Understand? In interval scale, I can do the difference, but I cannot do the ratio because of the arbitrary nature of the origin. In another case, I can only compare. In another case, I can only check for equality. Why is this important? If you have attributes you are collecting, if the attributes are not of the same type, you cannot perform the same operation on every attribute. Fortunately, in meteorology, that's not a problem. Why? I'm interested in the pressure distribution. I'm interested in the temperature distribution. Temperature, you are doing absolute scale. Pressure, we know what a zero pressure means. Humidity, zero. Everybody is agrees. Yes. So most of the variables of interest in geophysical sciences are ratio time. So you don't have to worry about the problems that psychologists have to worry about. So psychologists apply this, meteorologists apply this, but psychologists have a much larger headache. If you thought your problem is difficult, psychological problems are much more difficult. Ultimately, how do you compute similarity when I'm not in the ratio scale? Pardon me? Consider the right answers for that. So these are some of the extensions. We are already past 12:30. This I have about 90 per slides. Is a slide that I prepared for several lectures. I want to continue with this tomorrow. I also want to show you tomorrow the second lecture where we have applied these things to meteorological problems. All with me?
Yes.
Yeah. I'm going to give you, I have already loaded 3 papers that we have applied these. And Friday, tomorrow is Thursday, right? So tomorrow 2 lectures will occupy us with this. On Friday morning, we can have a general session for discussion with questions. The second lecture. First lecture, if there is interest, I can talk about things in data assimilation or whatever else you want to think about. I had requested you to tell Vinu about your choices of topics. I didn't hear anything from him. You asked me, but I wanted to tell him to coordinate with that. So you can still bring back questions on Friday, which we will try to answer. Are you with me? Are we doing AI now? How many of you believe we have started doing AI? Let's continue tomorrow. Thank you all. Have a good afternoon. Thank you.